Now that we know dielectrics are somewhat imperfect metals, when we talk about its ability to form induced electric dipoles. For metals, we have a lot of free electrons. So basically, whenever you have external field line, you can induce one electron. And therefore, by making metal having no field inside. But dielectrics are not that good in terms of its electric dipole inducing capability. So in this example, I have 7 external field lines, but I can only induce 3 pairs of electric dipoles. So basically, inside the dielectric, the induced electric dipoles are meant to produce counteracting electric field intensity. So inside the dielectrics, we always expect the field intensity, the amplitude, to be weaker as compared to my external field strength. So today we are going to try to find a way to mathematically formulate materials, dielectric materials, and we want to somehow compare, right, among different materials. So the first effort we're trying is to quantify the net electric dipole moment. So we're now trying to introduce a new vector field called the polarization vector, capitalized P with a vector sign. So this polarization vector is nothing more than the volume density of the sum of all the small dipole moments. So this non-capitalized P vector is the induced electric dipoles. So within every small value, you might have 10 pairs or 100 pairs of induced dipoles. They might be oriented in different directions. So the sum of all these induced electric dipole moments divided by your volume is thus defined as the polarization vector. So take a note on its unit. The polarization vector has a unit of coulomb divided by meter squared. So you might be wondering, aren't it defined as the volume density? Why not divided by meter cubed? Because P is QD, right? Q has a unit of charge, coulomb. D has a unit of meter. So basically you have meter, and then you have meter cubed. So 1 meter is being cancelled. So the unit for polarization vector is coulomb divided by meter squared. But the definition, the meaning is the volume density. Okay? Having defined polarization vector, now we're going to talk about the effects of the induced electric dipoles in 2 aspects. So whenever we have a non-zero polarization vector, that is essentially giving rise to some new charge distributions. So the first one is we're going to talk about the so-called polarization charge density, rho P. The underscript P denotes is due to the induced polarizations, and that can be viewed as a source of charge density. And then we're going to introduce a new vector field quantity. It's called the electric flux density, D, capitalized D vector. It is different from E. E is called electric field intensity, and D is called the flux density. The difference will be described in details later. But first, let's look at rho P. Whenever you have polarization vector having induced electric dipoles, you are contributing some effective charge density. And there are actually two forms. One is, well, whenever you polarize, right, by applying an external field, EXT, you somehow polarize or you align all these induced dipoles parallel to your externally applied field. So inside the material, things are all aligned, meaning it's polarized. So with P locally, each pair would be aligned, right, to your externally applied field. And each pair, even though your P is aligned in the direction of your externally applied field, but the field itself generated is reversed direction as compared to your externally applied field, right? So for this dielectric material, it has a finite size. Whenever the material has a finite size, you have boundaries. So in this case, on the top and the bottom, you have two surfaces. Okay? On the top surface, in the current case, because our externally applied field is pointing upwards, therefore making the top surface equivalently having positive surface charges deposited on the top. And on the other hand, for the bottom surface, it seems like I have induced a lot of negative charges. But overall, charge remains neutral, even though you have positive charges and negative charges, they sum up to 0, right? So dielectric materials tend to be charge neutral. Why do we have surface charge density? It's because we assumed in this case, this material is positioned in free space. In free space, you have nothing, so you don't have induced dipoles, right? And therefore, you have dielectric and you have free space forming the interface. So along that surface, you have exposed charges. And therefore, whenever you have induced electric dipoles and you have the interface, you are trying to create effective surface charge density. Okay, so for the first case is we have surface charge density induced by the polarization vector. So now we want to quantify it. Suppose my material geometry is defined by the black line. So I have two surfaces, the top surface and the bottom surface. But it is possible that my externally applied field is having some angle to my geometry. Right? It's perfectly fine. I don't really need to apply my external field, which is parallel or orthogonal to my geometry. Right? It's fine. So in this case, I apply my field so the induced dipoles are all aligned to my applied field. But that is making some angle to my geometric surface, right? So my geometric surface is, this is my surface, so this is my surface normal. Meaning that each pair of the induced electric dipole is having some angle to my surface normal. Alright? So now I want to talk about how to properly mathematically formulate the resulting surface charge density due to the induced polarization dipoles. Alright, so the total amount of charge over this surface, I can just form a box, right? A box with a surface area on the top and a very, very thin height. And I just calculate how much charge is being encompassed by that box. And now capitalized N is the charge density per volume multiplied by Q D, that is how many induced electric dipoles are encompassed by my box. But since they are oriented in an angle with respect to my surface normal, I have to perform a dot product, right? And then multiply by my surface area. So that's the total amount of electric dipoles effectively pointing in the direction along my surface normal. Okay? But this NQD is just my polarization vector. By definition, NQD, right? Okay, so I can reform this equation as the amount of charge enclosed is my polarization vector, making a dot product to the surface normal, and then multiplied by the surface area. Then by definition, surface charge density is delta Q divided by delta S, right? And therefore, it is simply P dot surface normal. So this is assuming the polarization vector is parallel to your externally applied field, but somehow your externally applied field is making an angle to your material geometry. All you have to do is you apply the dot product. This is almost like saying E external making a dot product with your surface normal. So therefore, if you have some geometry and you apply your field orthogonal to the geometry, you don't create surface charge density, right? To maximize your induced surface charge density, you want to make your externally applied field parallel to your surface normal. Okay? Again, the unit is Coulomb divided by meter squared. Okay? So this is the first time. Whenever you have induced electric dipole, you have the potential to create a new source of charge, and that is called the surface charge density due to your polarization. Rho PS. S stands for surface. So this is true even though for this material you have very uniform distribution. You have the same material, and each point you have dipoles. So even though inside the material, as a bulk, it appears to be charge neutral, but at the surface, you have the presence of the surface charge density. So the next terminology we're going to introduce is the bulk, the volume charge density. Is it possible that just by inducing dipoles, as a whole, we look from a microscopic view, the material appears to be charged? Is it possible? Let's look at this case. So we have some material, right? We have a very big material, and we're now looking at the microscopic view. This material is actually having maybe two different components. For example, salt and sugar. Is it possible? Of course, yeah, you can always drink salt plus sugar, right? You can just drink it. When we apply an external field, the ability to generate induced electric dipoles for salt and sugar are different. So in this case, the top material is more sensitive. It can induce more electric dipoles as compared to the bottom material. Okay? So for this case, as a material on the bulk, on the macroscopic view, because I have different materials making up this matter, I have some net charge within the material. And that is the origin of the volume polarization charge density. So this is telling you, if I have multiple components making up this material, I have an inhomogeneous material. Then, inside the material, I can always expect to find net charges. Alright? It's because we have incomplete cancellation. So the net charge does not go to zero. Right? Because we're dealing with an inhomogeneous material. Inhomogeneous. Meaning, the polarization factor for one point can be different from the polarization vector of another point. Therefore, this P is a function of space. But in the previous case, we have homogeneous material, so for each location, we have the same polarization vector. So basically, in this case, the polarization vector P is a constant. It's not a function of space. Alright? So whenever your P is a function of space, you're dealing with an inhomogeneous material, and therefore, inside the material, you have a way to form the volume charge density. Okay? Now, mathematically, all we have to do is we find the surface charge densities, the sum of the surface charge densities, and then we multiply by -1 to find this net volume charge density. Why? Look at this case. For each material, the charge remains neutral, right? Meaning, on the top surface, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positive charges. On the bottom of my material number 1, I have 8 negative charges. So for this given substance itself is charge neutral. And also for this case, I have 4 positive charges and 4 negative charges. So this P2 itself appears as charge neutral. This P1 appears as charge neutral. But looking as a whole, these two together, right? On the top, I have 8 positive charges, but on the bottom, I only have 4 negative charges. So I sum all the surface charges up, I have 4 positive charges. But I still need to remain charge neutrality, so the only chance is inside I have 4 negative charges. Okay? So that's one way to look at it. Another way to look at it is the net charge is not 0 because on the bottom of my material number 1, I have 8 negative charges. On the top of material number 2, I have 4 positive charges. These two adds up to 4 negative charges. Okay? Same result, but looking from 2 different perspectives. Alright, so all we have to do is, well, suppose we don't want to enter this material, we only want to observe it from the outside. So we count on the total number of charge at the outer surface. So QPS1 is this one, the 8 positive charges. QPS2 are the 4 negative charges. So I sum them up. And due to my understanding, it's just P dot AM, but this P for this one is P1, for this one is P2. Okay? This is like Gauss's law. It's exactly Gauss's law. Right? Over the closed surface, I'm trying to evaluate the total polarization vector, making a dot product to the surface normal. Okay? And then I can have this one, the integration over a closed surface, making the equality to the divergence of P over the entire volume. Do you know why I can draw the equality? You just finished your examination, but you're not getting away from divergence theory. This is where we can invoke divergence theory. Okay? Initially, you have surface integration over the closed surface, and now we transform to volume integration. And somehow we can relate divergence P to the volume charge density. Because by default, if I integrate over an entire volume, I have some net charge. That means I have non-zero volume charge density. Okay? So in this case, my QP, the net charge, is the sum of my 2 surface charges, but I have to multiply by a negative sign to maintain charge neutrality. Okay? So I need to take account of the negative sign. And that is simply negative divergence P. Okay? So in this case, whenever we're dealing with inhomogeneous material, meaning polarization vector itself is a function of space, then we perform its divergence and we multiply by a negative sign, we have the resulting volume charge density. Think about it. Is it making sense? Why do we have a non-zero volume charge density? due to polarization. It's because we know that we're dealing with inhomogeneous material. For inhomogeneous material, polarization vector can be very different for different locations, right? And that is telling you this P vector is a function of space. Therefore, whenever we're trying to perform divergence, we're trying to calculate the differentiations of P, right, in different unit vectors. In Cartesian coordinate, x, y, and z, you're all trying to find their changes, right? It makes perfect sense. If P is not a function of space, meaning you're dealing with a uniform material, P is a constant. Divergence of P in that case is 0, right? So whenever you're having a homogeneous material, you don't have volume charge density, okay? So you have to be able to connect these dots together to form a line, so your understanding is deeper and more thorough, all right?